Perfect. We're going to get started. Welcome, everybody, to our workshop. This workshop will be covering some computer vision techniques. In particular, we're going to focus on some object detection and segmentation model building. And basically, you will learn how to do it from scratch, from end-to-end pipeline, from starting from preparing the data set, training the model, testing the model, and then we're also gonna cover some tutorials and resources for converting the model to iOS. So without further ado, let me first give an introduction to my co-presenter and I. My name is Cody. I work at the Home Depot as a data scientist. And presenting with me is Eddine. He works at LVMH, and he's also a data scientist. Yeah, and we'll get started. So if you, does everybody have the link that I posted to GitHub? And then you can go here and then download the overview slides so you can follow some of the contents over there. And then there are some links that are useful in these slides too. I'm gonna repost this into our chat. Yeah, thanks for the comment on the background. All right, so we're ready to go. And like I said, you'll be learning to perform an end-to-end image segmentation pipeline, where we'll cover all these aspects, including dataset preparation, model training, post-processing, and conversion to mobile. So here's the agenda. We'll start with introduction of the techniques in modern computer vision and deep learning, and Eddine will be covering this section. And then we'll go on to data pre-processing and customization, where we will basically download a very popular computer vision dataset, which is open to the public. And then we'll do some pre-processing and customization on it. And then we'll take a 10-minute break. If you have any questions or concerns over that period, please feel free to chat. And then after the break, we'll go on with model training, validation, testing, post-processing and refinement techniques, and then cover some contents with mobile conversion. And then we'll leave about 15 to 20 minutes for Q&A. And just before we start, if you have a Linux programming environment, you can basically follow along the entire tutorial with no issue. Especially if you have a GPU, then you can actually follow the entire content. But don't worry if you don't have a GPU, because in the model training section, where the GPU is needed, we have also prepared a different version, which you can run everything in Google Colab, so you don't need a local GPU on your machine. For the rest of the sections, if you want to follow along, if you have a Linux environment, that would be the best. If you have a Mac environment, it should work too, with all the installation environments instructions that we provided. And before we start, if you can open this Colab link, because the installation process does take a little bit of time. So if you can open this beforehand and then execute the first 2 cells for the installation, then once we get there, we'll save some time. Yeah, but if you missed this link, I'll post it in the chat as well. And then, okay, so I'll also repost the GitHub link. Oops, I think I posted the same link twice. So the GitHub link, okay. Yeah, so there you go. You have the Colab link and the GitHub link. And then this overview slides here will have the contents that I just showed. So you can also access the link through that PowerPoint. All right, so Eddine, take it over.
Thank you, Cody. Thank you very much. So this is our repo. Basically, we'll start with the first chapter, the introduction. So we will present on a Jupyter notebook. So this is a new way to present rather than slides. I just want to say something over here is basically that the area of computer vision and what we are going to present, it basically deals with anything that humans see and perceive. So there are so many tasks that we human and we do automatically or subconsciously that we hardly think are even worth mentioning. So, however, for a computer to learn, to perform, or even to try to mimic these things, this is really difficult. So basically, imagine looking outside your window. What do you see? Maybe you are sitting in an office building and see traffic outside. Maybe you are on a vacation and see beach or mountains or a forest outside. So do you ever wonder how you recognize something or someone? How do you know when you look at someone and know who they are? So without thinking about it, we first identify object in any image that we see. Then we try to find what relation exists between object to identify the scene or place. Only then do we get an idea of what is happening in the image. So sometimes we also look at an incomplete image and we use our knowledge and experience of what we saw before in order to determine what is missing from it. So all of these are computer vision tasks, what we are doing as a human. And the aim of this workshop will be to demystify and explain some following computer vision tasks, like object detection, image classification, face recognition, because it's the face for us is an object, instant segmentation, and semantic segmentation. What is not going to be demystified is another task called basically a visual relationship detection. So if you have a table and you have a cup, so the cup will be on the table, and this relationship is also could be explained using machine learning. Also image captioning, so how you can describe what is happening in the image using text. And finally, image reconstruction or image embedding using usually done using techniques called GANs or generative adversarial network. So I just want to start with this very famous image over here. If you can tell me in the comment, what can you see in this image?
A rabbit.
A rabbit, okay. As you see, so some of you see a rabbit, some of you also see a duck. But basically, depending on how you look to the feature, for example, if you are looking, this one is the eyes, and this is the mouth, etc. So this it will be classified as a rabbit. But if you look here, this is the eyes, and this is the front of the face, etc. So you will look at as the duck. So even you as a human, you can have this mislabeling of different images that you can see. This is the same image, but based on the feature or feature detector or kernel that you are looking, or what you see from before, or how you look to the duck or the rabbit, you will classify this as duck or rabbit. This is actually what deep learning and CNN models are doing. The idea over here is that you have this system that contain a different aspect of convolution, polling, ReLU layers, etc., in order to finally classify if this is car, truck, van, etc. So this is how it works. Basically, you have a feature detector, as we said. It could be eyes, it could be ears, it could be mouth, etc. And we have the image, which is this one. Image, of course, here encoded as a pixel between 0 and 1 in order to facilitate stuff. And this feature detector will goes around all the image like this in order to detect where we can find this or sometimes we cannot find this feature detector. So that classification will be changed based on the placement, but also based on the existing of that feature detector. So just to repeat, feature detector, or we could call it the kernel or filter. It's basically how we can detect this stuff that will specify the class of the object. And here we can also see something very easy. So this is MNIST dataset, which is to classify number from 1 to 9 as the right number. So here I will just draw a number, let's say 3. The first guess, it was 3, and the second guess was 8. And as you can see here, this is the first feature map, and each feature map will be related to a feature detector. For example, this, as you can see, this is detecting the horizontal edges. So if you have horizontal edge, it will be detected in this feature map. If you have horizontal edge, it will be detected in this one. So as you can see, like we have different features related to what we are able to train. But here the idea is all these feature detector are automatically created or automatically extracted from this image. Of course, via training on 1,000 or 2,000 images in order to get this feature map. And then we do max pooling. So you can see we preserve the detected edges, but with smaller neurons or smaller features. Also, we can do another layer of convolution and then map, and then we have a fully connected layer at the end in order to help us to define what are the neuron that that was being fired in order to have this classification. And finally, we can have the final classification as 3 over here in the final fully connected layer that will contain 10 images. Of course, this is a cross-validation, uh, cross-entropy, categorical cross-entropy final loss. Saying that, we can move to image classification. So as we said here, we have this MNIST dataset, which is a very famous dataset, especially in research, in order to test different architecture and classification models. We also have other benchmarking dataset that we can test. We can also move to object detection. So here, this is another task that we will demystify in this workshop. So object detection here is the task of image classification, but with localization. So we don't just tell you that this is a plane, that's it, but also we tell you, okay, this is the placement of the plane. So we will draw a bounding box around the plane in order to tell you where is the exact location of the object. We have also image segmentation. So here in the object detection, we just draw a bounding box, okay, around which is a rectangle around the image, but it's not too precise. We want the exact colorification or the exact segmentation of the object. Here, we have to use image segmentation. Of course, there are two types of image segmentation. We can have semantic segmentation and instance segmentation. And finally, we can also discuss about some general structure of the image segmentation. So basically, usually we have encoder and decoder. So the encoder will encode the image into a coding layer in order to have all the information into one vector representation, call it embeddings. And from this embedding, we recreate the image again, but based on the instances that we can segment using this input image. For the fully convolution neural network, so it's you can even discern it from the name. So it's a fully convolution network, which own their name to their structure. which is built only from locally connected layer, such as convolution, pooling, and upsampling. No dense layer, so we'll not have this last layer that will predict the class. Which this reduce the number of parameters and computation time. Also, the network can work regardless of the original input image, so you don't have to resize the image to usually to 512 or 260 or any type of resizing that we need to have. So also we have Segnet, which is also another encoder decoder network. UNet, the only difference here is we have to concatenate the encoder feature map to upsampled feature map from the decoder at every stage. So here we have a connection between the first layer to the last layer in the decoder, also the second and the second layer in the decoder. For the deep lab, also this is another improvement for the image segmentation, also based on the encoder decoder layer. We can also find the PSPNet or pyramid scene parsing network, which is a semantic segmentation model that utilizes a pyramid parsing model that exploit global context information by different region-based context aggregation. The idea here is that the local and global clues together make the final prediction more reliable. PSPNet also use pre-trained CNN with the dilated network strategy to better extract the feature map. And one of the most famous model is the mask RCNN model. Mask RCNN has been, I think, the new state of the art in terms of answer segmentation. Of course, there are like a rigorous paper or improvement to the original masker CNN. Also, there are some easy to understand tutorials. I can share with you later some of them. Also, some good quality open source codes around for your reference. Here, I want to share some sample understanding of it. To give you a first look, Masker CNN is a deep neural network aimed to solve answer segmentation problem in computer vision. In other words, it can separate different objects in image or video or any type of input. You give it to an image, it gives you the object boundaries, but also it gives you the box, the class, and the mask around the object. So there are two stages of masker CNN. First, it generates proposal about the region where there may be an object. Second, it predicts the class of the object, refine the bounding box, and generate a mask in pixel level of the object. So both stages are connected to the backbone structure. The backbone could be ResNet, ResNet, XNet, or DanceNet, so any type of backbone. Then we have also Cascade RCNN, Mask RCNN, which is an improvement of Mask RCNN. HRNet model. This model usually maintain high resolution representation through parallel multi-resolution convolutions, which is really amazing. The application here are mainly self-driving vehicle, face detection, medical imaging, video surveillance, or any use case you can think about in order to improve your way of working or any type of computer vision model that you can think about in order to improve your business. For the dataset, of course, in order to train this model, there are many vision datasets out there. Like the city space, which contain 30 class in urban street scenes. So you can train if you want to create a self-driving vehicle model. There is also Pascal dataset, Coco, which is very famous with 300K photo and 40 scene category. And also, these are benchmarked datasets, so used almost in every computer vision papers. But there is also some private or like public-private dataset that you could find it in Kaggle. So Kaggle, which is one of the most famous platform in the machine learning and data science area. And finally, we have ADE 20K dataset that we will be using in our workshop today. It contains 3,000 object classes across 1,000 complex everyday scene. You can see here examples. So this is interactive ADE 20K dataset from MIT, and you can search for your object. For example, let's say you want to detect a window. So you just have to check what are the images related to windows, and you can see thousands and thousands of images that contain object segmentation or object detection of images. You can also do usually selling, for example. If you do selling, it's quite difficult, like floor or selling, it's quite difficult to segment. So even if you want to do your own labeling, it's quite difficult. So you can see here, okay, so it's not working. Okay, so you can see here some object detection of selling, but also what you can also detect is the scene. So you can detect indoor scene, or let's say here. So you can select the indoor, but also the object. So both of them. So you can basically diversify your image input in order to not bias your final prediction based on the use case that you are working on. So if you are working inside your home and trying to detect different objects, it's better to detect object inside the indoor scene provided by ADE 20K dataset. Saying that, I can move the microphone to my co-host Cody in order to continue the workshop.
Right. Thanks, Eddine. Great intro. If everybody have any follow-up question, feel free to chat. I think Eddine can reply in the chat box while we move on to the next chapter. For the sake of time, we actually didn't cover in detail all of the contents related to each of these topics. And we also prepared some slides here, which has more content and links to different papers, to the different techniques. And if you're interested, please download this and check it out. Yeah, and as Eddine said, we'll be working with the ADE 20K dataset today. So this is a very, very powerful dataset if you use it properly. One, because it has a lot of different training images. Two, because it covers a wide variety of scenes and different categories of objects. And three, there are just a lot of tools out there that can handle the very accurate and detailed annotations on these images. So before we get to work with this data set, if you have some time and if you have a fast internet, you can try to download this data set. Once you check out the repo, you can cd into this dataset directory, and then you can download this dataset using these commands. And then this way you'll be able to actually follow through the code, run through the code. But it's not necessary because in chapter 3 we'll be using the pre-processed zipped dataset here. So you can use them directly if you don't want to execute the code right now, because this does take quite a while to download and extract, and it takes up a lot of space on your computer, obviously. So let's get into the code. First, actually, what I want to do is make sure that you understand how great this data set is. As you can see there, if you go to their website, there's a link to the full data set, which is 3.8 gigabytes. And there's actually a smaller data set called the MIT Scene Parsing Benchmark. And if you go to this one, you can actually see it's a much smaller data set. And the difference between these two data sets it's actually not very clear if you don't read their paper. Oh, oops. Host disabled. I can't share screen. Let me. Yeah, thanks for reminding. Let me. Yeah, we can take some time to answer some questions first. So I think the Colab code is right here. So if the host could let me share screen, that would be great. Check.
I think you are the host. Yes.
Oh,
no.
I don't think so. Let me.
Okay.
Yeah, I was able to share. Okay, there we go. Now I should be. Oh wait, host disabled screen sharing. Okay, perfect. Now I'm the co-host. All right. Sorry about that, everyone. Let me. Yeah. So if you so somebody said they get they try to access the Colab version, they get a 404 error. If you click on this link, it should work. And yeah, I just posted up there again. You let me know if it still doesn't work. We'll figure it out. Yeah, but like I said, you can see there are two different versions of the AD20K dataset. So there's a full dataset right here, and
Cody,
there's a scene.
are you going to share something?
Yeah. Can you see my screen or no? Still?
No.
It says I'm sharing screen. Okay, that's so weird. How about now?
Yes.
Okay, perfect. All right, so now you can see it. Third time's the charm. Yeah, so there's a full data set and there's a scene parsing benchmark. If you don't read their paper, it's actually not quite clear what are the differences. But basically, what's happening is that a lot of the current literatures out there, they actually only use this smaller scene parsing benchmark data set because a lot of these classes in the full data set, it only covers the small areas of the image. So basically, what they did in this scene parsing benchmark dataset is that they removed those smaller classes, like for example, electrical outlets. They're really small in an image, so they don't cover up a lot of the areas. And then they basically set a threshold and removed those smaller categories from the full dataset. But today we're going to actually work with the full dataset, and we're going to observe how great it is. But if you're just looking to train some smaller models with more of the bigger classes, you can also use the scene parsing one. So now let's move on to the GitHub code. If you open chapter 2, reprocessing, this is a notebook that we'll be going over through. And some of you might have missed the part about downloading the dataset. So if you if you do want to follow through and execute these code yourself, you can cd into the dataset directory and then download this dataset. Yeah, and after this, you'll be able to follow through with these code. All right. So these are just some of the packages that you need. It's very simple, basic packages. The conversion is the script that we wrote with some helper functions that does all of the conversion and the customization of the dataset, which you can find also in our repo under the same subdirectory. And we'll go over this example first, and then I'll go back into the conversion code to go through some of the important functions. So first, we set some directories, which are the source directory and the destination directory. So these are basically the raw dataset directory, and then after you convert and customize your dataset, you'll be storing the new dataset in here. So what we do here is it's a very simple interface. We built using this conversion script. So all you need to do is to select the scenes of interest to keep using these keywords, and these scene names you can basically select these scene names based on your use cases, and then from you can either go into the data set to find out what the scenes are, or you can actually just use your browser to browse through all of the different scenes that you're interested. Yeah, I think there's a link. So if you just, for example, right here, we said bedroom, child's room, dorm room, hotel room. And if you're interested in any other rooms, you can go to this browser here and then type in, for example, dining room. And then, yeah, so there's a scene like that, and you could add it into this list. And then you can also reject some keywords like outdoor. So if you, so this is just removing some of the included scenes from this list right here. So some of these scenes actually also they're named an outdoor scene. So if we want to remove this here, we can also reject this keyword. And then this next section basically allows you to specify the list of classes that you're interested in training on. So this list here is just what we came up previously. For each of these groups, you can also group them together. So what we did here is that we're grouping all these three into the same class, and then we're grouping all the bed, blanket, cover, headboard into the same class. So basically, this is a way of, if you don't have so many requirements on segmenting all of these different objects, you can combine them into a single one. So in your final output, you'll see these objects outlined within one segmented area rather than several different ones combined together. And then the next step is we just call this function, and then it will do the conversion job for you. And then you can visualize the segmentation mask using some of these code below here. So this is actually using the PyCoco tools, which is the standard function for visualizing a Coco dataset. And the Coco dataset is a smaller dataset than 8020K, but it's sort of the the most popular computer vision dataset out there. So a lot of different modules and tools out there are very mature for handling the Coco dataset. And then a lot of the datasets are also using Coco as the middle ground, the middle format when you try to convert your own dataset into Coco format, and then you can execute different modules here. So this is what we do. And we use the Coco visualization tools here to visualize our data set. So what you do here is you basically just specify your annotation file, which we obtained through this function. And then we can load some of these classes and categories. And as you can see, we combine some of our subclasses into bigger classes. And then these are all the final categories that we have listed. So we just show some random samples below, as you can see. We basically, this is an example of the bed sheets and headboards and bed converted into a single class, which is sort of in green. And then you can see the pillows, you can see the lamps, doors, storage boxes. Yeah, so if you have some time, you can definitely run through this code. It should execute pretty fast. And then as I go through the conversion code, you can try to play around with these code yourself and maybe create your own customized data set. Don't worry about changing any of these because even if you change it and you you use your own data set here. You create your own customized data set here. In our code, in our training, in our model training session, we'll be using this version here. So we'll have a zip file for you to download and then load into the model. So you can play around with these yourself. All right, let's make sure no questions so far in the chat. All right, Eddine, if you look at any questions, feel free to answer them. And then, yeah, I'll keep going here. All right, so now let's move into the conversion code. Basically, this file just contains a lot of the helper functions that we were using in this notebook, and it's a very handy script that you can actually modify to fit a lot of different other data sets, because we want to convert into the COCO format. There's a lot of common fields in these annotation files where you can just transfer very easily. But let's look at this first. So this first function, filter AD20K dataset, basically just takes in these keywords that we just mentioned, the different categories, and then it narrows down this dataset for you. So we basically go through these go through this entire dataset, and then we search for the names of the categories, object categories, and matches these required keywords, and then remove all of those that are contained in this list. So as you can see, we have the matches and the reject matches, and then we basically do some string processing, and then output the final metadata, which contains a dictionary of the final list of categories that we are left with.
Cody, do you have a conda or requirements file? This is asked by Alesh.
Oh, let me see. We should.
Yes.
So actually, if you, let's see. So these should be all standard. And then if you, I think OpenCV is not there, so you can just do pip install on OpenCV, or pip install CV2, and then pip install PyCoco tools. But don't worry about if you encounter some errors, feel free to post in the chat. For all these packages, it should be pip installable. We do have another setup in chapter 3 during the model training session, where we provide more guidance on how to install the packages necessary to train the model. But for this chapter, all you need, I believe, are pip installs. But yeah, do let me know if you encounter any error and can't do pip install, and we'll provide more guidance. Hopefully that helps. Let's see. All right. So let's keep going for the sake of time. So the next function is get new label mapping. So what this one does is basically after we create the subset of dataset of this dataset, we need to remap these labels. So each of these labels, these categories, have a numerical representation. So what all this function does is that the original numerical labels for the original categories will be off once you select your subset of data. So we basically remap them. For example, the original label for bed might be 36, but when we have 20 classes in our new subdata set. And then what we do here is we just move that 36 to, say, 15, based on what the sequence of that of the original label is in that entire sequence of categories. So it's just basically remapping all of these labels. And then the next one is display segmentation. So what this one basically just plots these. This is a helper function to to show the random random sample here, where we can see these visualizations. And then the create. So this one is actually let's see if we have enough time to cover this a little bit. Actually, yeah, we do. Okay, so this is all for AD20K to the Cocoa version. This is all just the pre-filtering of the different categories. Where we're actually doing the transforming of this data set, we have it below. So let's skip this part first, which deals with VOC. And let's look at the Cocoa dataset format. So if you move down just a little bit, you'll see how we transform the dataset into the Cocoa format. So first function, very simple, just creating the directories and listing out the files that we're going to output the annotations to. So these are the annotation files. And then second function, create Cocoa image info. So this one is one of the key functions here. So this is creating the metadata part. So the Cocoa dataset not only has the sort of the essence of where the segmentation lies in for each of these images. It also has all of these metadata, and these are very important because each of these metadata helps the model and all of those tools out there to recognize what your image, where your image is, and what the width and height. So your segmentations will actually match with based on these dimensions. And then these IDs and file names will be also important for you to select and visualize individual images, and then for the model to basically train, test, split these annotations as well. And then the process Cocoa sample. So this is actually the essence, sort of where how we transform the segmentation, format. So the AD20K segmentation format is different from the Cocoa segmentation format, and this is where we convert between the two. So this function takes in the entire image directory, the metadata, the label mapping that we did up there, and then the image file path and the segmentation file path, basically the annotation file path. And then here, so you don't have to worry about all of these here. These are really just setting where your file leads to at the end. And then you want to look at this for loop right here. So this is where we're actually doing the transformation of the segmentation. And as you can hear, so the first one here is we get the pixels corresponding to the instance ID. So each instance ID is one instance of the segmented object in each image. And then we get the pixels. And then here we do some color channel manipulation in order to get the correct mask, in order to get the correct segmentation mask. So this code was adapted from this link here. It's a MATLAB code, so it's kind of esoteric if you don't if you don't know MATLAB. But basically, what this is doing is taking the red channel value, and then this red channel value basically represents the old label ID for that category. So think of it as they use this red channel to represent your label ID of that object. So this is how we retrieve that old ID, and then we map it to the new ID based on the dictionary we created above. And then here is what where OpenCV comes into play. So what OpenCV does here is that it gets the bounding box for that segmentation. So we may have not reminded you this, but segmentation is basically once you get the segmentation, you can also get a bounding box. So segmentation is usually considered a multitask model. So not only you get the bounding box of your objects, you also get the exact pixel classification of that object. So this is where we get the bounding box. And this is also a necessary field in the COCO format dataset. Next, so this is where the segmentation conversions is actually happening. So these pixels are segmentation, and then the RLE format is what the COCO format of segmentation is using. So we get the RLE format using this COCO mask tool. This is from I believe this is from the PyCoco tools, and then we got we do count decoding. So if you don't do this, it will have a different encoding than the COCO format requires. So we need to do a decoding right here. And then finally, once we have all this information with the ID of the object, with the bounding box of the object, and the segmentation of that object, we put it together into this annotation field, and then assign all of these IDs, assign these areas and bounding box, and then we're finally done with this one annotation. And then this entire for loop just loops through all of these instances, and then create this final annotation file. This is a really complicated function, and but it is definitely the essence of it. So please make sure if you want to, especially if you want to modify it further for your own usage, it's definitely recommended that you can understand this function really well. All right, so after that's done, all the rest is pretty easy. So convert to COCO just uses all of the functions where we talked about above, and then it takes in these directories, required keywords, and then outputs the annotation file. And that's basically it for conversion to the COCO format. I think we might have some time to briefly go over the VOC format, which is a little bit different conversion process, but we also provided the conversion code here, so called pre-processing VOC. So it follows sort of the same, as you can see, it follows the same structure. It just calls the different function. It just calls the convert to VOC function, which is get VOC label map. And then, as you can see, it's a little bit of a different format with the segmentation. But once we convert to COCO, they will actually be all the same, the same format. So we're going to briefly go over these functions in the conversion code, and then we'll basically cover the differences. So this part is pretty much the same. We do the we create so this is the overall function and doing the old to new ID mapping, and then creating the directories.
Cody, we have a problem to clone the repo.
Oh, really? So what is the question? Failed to clone chapter 3. Segmentation and detection a second time aborting. Cloned it anyway. Okay, maybe try again. Cloned it anyway. Actually, if it doesn't work for chapter 3, it doesn't really matter. As long as you have chapter 2, chapter 1 and 2, it should work. Because we're gonna go over in chapter 3, we'll be using the Colab version. All right, okay. Awesome, perfect. Okay, so VOC format dataset, we're gonna basically take a quick look here. So as you can see, we didn't need to do the complicated process of converting ADE 20K to COCO. But this is the overall function first. And then what this one does, it's really just getting the label mapping and creating the directories. And then for each of these VOC mask, it uses this create VOC segmentation mask function. And then it's so the only key difference that is worth noting here is that the VOC mask uses different sort of a different color channel mapping, whereas the COCO format, whereas the AD20K uses the full 3 channels. The VOC mask is actually a single channel mask, which is the key difference here. And then you don't need to understand all of these parts, but I would definitely recommend you to actually check it out. Check out the VOC dataset on their official website and see if you have any questions, and feel free to ask me here. But for the sake of time, we're not going to go into more detail with the VOC because it's a rather small dataset compared to AD20K, and we won't be using it for the purpose of today. But one more thing I do like to go over is, in a lot of cases, you actually want to create your own dataset. So if you really want to, like, say, create something like that's not within the 3,000 classes of AD20K, or maybe if you're looking for a more say style-specific dataset. For example, in the AD20K, you have a lot of these scenes are quite old homes. For example, if you're looking at all these chairs, tables, or even, like for example, we can look at a refrigerator. So as you can see, a lot of these are really old. And say if you want to create a new data set with, like these stainless steel appliances, you might want to create your own data set. And we have a lot of tools out there, Mechanical Turk, we have Label Me. And this is just an example that we provided here where we're using Label Me to create a cat data set. So in this toy data set, we just did the labels ourselves. We uploaded some cat pictures, and then we also draw those labels. And then these labels have, so basically cat ears. We're trying to identify where the cat ears are. And then if you look at if you're interested, you can look at this function here, which is converting the label me format to COCO. So a lot of other tools, they use a similar format to label me. And even if they don't, you can always, there are always tools there to help you convert from your own format to the label me format. And then once you have that format, you can use this function to create your own COCO customized dataset, where like the key functions here are, again, the converting the segmentation format. So a lot of these are just polygons where you draw with the different points. So when you use these tools, you're using the polygon tools where you have just the different points. And then basically converting that area to the segmentation. So the key parts would be right here. Yeah, but we won't go into the details here. Definitely try it out if you're interested. And feel free to ask us any follow-up question if you encounter some difficulties. Let's take a few minutes to answer some questions with this. And oh, okay, so someone asked, what's the intent of converting VOC and AD20K? Let's actually go to the first question. The VOC only deal with black and white. No, it does not only deal with black and white. It deals with, let's see, 255 levels of black and white. So you can think of it as a single channel mapping for the different colors of the different colors mapping to the different categories. So it can cover up to 255 different categories with a different level degree of black and white. So it's single channel, but it doesn't deal only with black and white. So you can think of it, even if it's in a green channel, you can be like, from light green to dark green. The black and white is just a sort of a standard when you think about it. And then what's the intent? Yes, exactly. The intent of converting VOC and AD20K to COCO, great question. I think I briefly talked about how COCO is like the most popular format currently out there. So a lot of the different repos tools out there, a lot of object detection models, segmentation models, they all use the COCO format as sort of the standard format that their models deal with. So if you can convert your data set like VOC 8020K or the custom data set you created using label me to COCO format, then you can directly execute their code, build their models using that Mado format dataset. Using your own dataset is also a possibility. So if you want to use those formats directly, you'll still have to do some conversions. And it might be a lot more complicated than just transforming your dataset directly into the COCO format. Hopefully that answers your question. And did anybody get a chance to run some of these conversion code by any chance? I know it takes a long time to download this full data set, but definitely let us know if you run into any errors. We tested this in our Linux environment, but yeah, we didn't get to test it in a lot of different environments. Okay, perfect. Chapter 2 run for you. That's awesome. So yeah, so like I said, the Mac OS Linux should all work because these are really just standard libraries that you can pip install, and it shouldn't cause any errors. But it's good to know that actually works. Okay, perfect. Let's see. Should we move on to chapter 3? Does anyone have any lingering questions before we move on to model training? All right. Actually, I think we're supposed to take a little break right now. Yeah, let's take a little break and we'll be back around 2:05, 2:10. And make sure you go to this link and execute the 2 cells. Oops, mine just disconnected, but no worries. Eddine will be leading this section. Just make sure you have some time to execute these first 2 cells here to do the installation.
Absolutely.
All right. See you back in 10 minutes.
Maybe I will just show you how you can basically have this. One moment. Can I share my screen? One moment.
Oh yeah, go ahead. Definitely. Take it over.
You need to turn off your sharing.
Oh, okay. Pause share, stop share. All right, can you do it now?
Yes. Okay, so just you have this our repo. Okay, you copy the link from the repo. You go to Colab. You just click Colab, research.google.com. Okay, then you go to GitHub. You just put the link there, and then you go to chapter 3 training segmentation, and then you have our model. So basically we are going to use tutorials. So just go to Colab chapter 3 and 4 detection tutorial. You just click there and it will open directly for you. And just run the first and the second cell. Yeah, that's it. You can share back, Cody.
No, you're going to take over chapter 3, so you can keep sharing. Actually, I'll open the PowerPoint for everyone.
Yes. Is there anyone who have a question for us about the topic, about anything?
Yeah, feel free to leave in the chat too. We'll just be on a break for 10 minutes.
If anyone want to speak, we can give him the mic as well.
Oh yeah, are they allowed to talk or no?
Yes, why not?
Okay. Okay, maybe they can't unmute themselves directly.
I can unmute.
Oh, okay. Yeah, if anyone has questions they want to ask in audio, just let us know and we'll unmute you.
I think everyone understands everything. Are you still with us or no? I think we lost them or something. Ah, okay. Yes, so there are some OCR projects done for the CV, the resume, if you want to basically analyze automatically different resume that you can extract. And the idea is basically the main problem is usually how you can detect each section inside this resume. So there is either a resume or there is the receipt of someone who go to the supermarket and he want to analyze everything like tax, net price, breed price, etc. And usually there are like different data set that you can use in order to detect different aspect of this paper or this document. And yes, so we can do it, but it depends on the distribution of your data set. Of course, if you will provide something very different in the test set, it could be problematic for the object segmentation, because usually all the CV, for example, could be different with different designs. So sometimes you can find his city or his number on the right, so sometimes on the top left. Sometimes the skills are in different places. But there are some model, even not with CNN, with the LSTM, where you can basically try to extract the text and then try to reason from this text in order to understand what is this section is about. And basically you can extract different component from this CV in order to analyze it automatically and provide the best talent or the best profile for the managers, etc. Yes, of course. So for Guillaume, sorry, for Rajiv, I think did I answer? Okay. For Guillaume, is there object detection segmentation data set for drawing or painting, not photographs? Of course. So there is one type of photographs. Imagine that you have two type of data set, one which is a real life image and the other it's drawing. So this network will help you to get as an input the real life image and give you as an output the drawing. So imagine like you have 1,000 pair of these two images, like original image painting, original image painting, original image painting, and the model will try to learn how he can move from this space of original image into this painting. So in the inference in the future, whenever you have a new image with basically a real image, you can go directly to the space of painting or drawing. And you can do this with generative adversarial network, but also there's some style network that you can do. So basically here you are applying style that you have. I think I have something that I can share about this style network. So basically what you can do is as this. Basically, you have input image, which is the style. that you want to apply on the original image, and based it on this style transfer network, you can get this image as similar as possible to this style. Okay, so yes, but also there is the drawing that we discussed about in painting. For example, you want to do in painting using guns. I think there are a lot of network here. Sorry, with guns. And you can see here, for example, if you have a missing value. So imagine like this is your input image that you want, which is the original image or ground truth. And this is the input image to the model. And you want to inpaint this as close as possible to reality. So this network is always the same. So you have your input image, you have another missing data image, and you try each step to inpaint with the most closest to the original image. Or for example, here it will also try to inpaint with the most closest to the original image. For example, here you will get the eyes, or what will be the most possible hair to the person here. So yes, so inpainting is one of the key tasks that you can do with the CNN model, and more especially with generative adversarial network. I can't see if there is any other. Yes, and the recording will be after the conference, I believe. I'm not sure about that, but maybe Cody can confirm that.
Yeah, I think the recording will be available after the entire conference.
Usually, I think the most important problem is not even the modeling phase, like how you can train the model, because even what we are going to show you later with detection, you will see that it's very, very easy to train a segmentation model. I think how you can process your data, how you can create your training data and change with different format, it's the critical aspect, because sometimes you have annotation which is not in Cocoa format. So how you can convert your annotation, which is sometimes unique, and how you can convert it to unique. So I think we have some problems with OpenCV here.
Yeah, I think it should be OpenCV Python. I think I said pip install CV too. That was my bad. Yeah, thanks for taking all the questions, Eddine. Wanted to give a quick addition on the question regarding the different sections of PDF forms. Yeah, it's definitely available. So it depends on your use case too, right? If you're looking to identify specific fields, like you're looking for like the name field or like the age field, that's a different application. Say that you want to identify the exact writing on it, but I think it's sort of like a two-stage process where you identify the which box that you're looking at first, and then you identify the specific writing. So these are sort of two separate tasks, and you probably need multiple models to deal with this. And let's see, any other question? Painting or drawing, I think the lady answered that really well. Okay, cool. I think we can begin chapter 3 training now.
One moment.
And by the way, if you want to have it easier way to the collab, you can also actually open this, and then the link should be right on the top. You can just click right here, open collab, and get there. if you're confused of how to get there in the future. Yeah, it's right here. Oh, oops, I didn't share my screen again. So let me share it. Yeah, so if you're if you're confused about opening the link to the Colab notebook in the future, just go into this Colab chapter 3 and 4 here, and then click on this, and it will lead you to the Colab version of the notebook.
That's more easier.
Yeah. Just
okay.
yeah, it was just a little bit confusing to me at first too, of how to actually get there. But there you go. All right,
Okay.
Eddine,
Should I
take it
share my?
over.
Yes. You need to stop sharing.
Okay.
Yes. Okay, so we will start chapter 3 for the moment. So thank you, Cody, for all the presentation that you did. Very interesting. So in this part, we will basically show you how to execute the segmentation inference with detection detector object. Next, we will train a new segmentation model detection with a new customized subset dataset from ADE 20K dataset. And finally, we will run model inference and image post-processing later with Cody. So basically, we need to start installing NCCV compiler by NVIDIA, which is intended for use with CUDA. CUDA usually runs on both CPU or GPUs, but it's more faster, of course, via GPUs. We need also to install PyTorch, which is our backbone training that we will use. And we need also to install MMCV, which is a foundational Python library for computer vision research, and it supports many research projects. Basically detection, and then detection. So we need to git clone it, and then cd detection, and basically install it. For those who don't know, detection is so great. Why? First of all, it's an open source object detection toolbox based on PyTorch. It's part of the Open Lab project developed by Multimedia Laboratory. It is faster in training and inference than many other code bases like Facebook detection, masker CNN benchmark, and sample detector. They have decomposed the detection framework into different components, and one can easily construct a customized object detection framework by combining different models. It also supports training on multiple GPUs. So if you have like NVIDIA DGX, you can basically train your model on multiple models. And you can see here, you can see basically different baselines like AirPN, basically the region proposal network. You can see by faster RCNN, masker CNN that we presented before, faster SRNN, etc., etc. So there are like thousands and thousands of models that you can do, and all of them are implemented with the same way. So if you have your input data in a COCO format, you can train all these models, benchmark them, and you can also see YOLO, the famous you look only once version 3, and different other data set. And we can see also that I think we can see what are the backbone used. Okay, one moment.
So I think if you go to their model zoo, you should be able to, yeah, there we go.
Okay, I think I will just go to detection. Yes, so here you can see all the model that you can use as
yeah, the
model
zoo
zoo.
right there.
Yes.
Yeah.
Ta -ta 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 -ta.
So I think this is easier here. I find this easier than their documentation. I don't think it's maintained very well. So if you go into all of these different networks and backbones, so for example, if you look for, yeah, like
Yes,
ResNet,
yes, so the
HRNet.
backbone supported, as Cody said, are ResNet, XNet, VGG 16, 19, or any type of models. You can also find HRNet, RegNet, Res2Net. So, and the idea over here, why it's better to use detection. They are maintaining the latest backbone and the latest architecture for segmentation. So whenever there is a new model that provides with better accuracy, better loss, better um, uh, uh, basically classifications, metrics, you can just change the modular representation of their structure, and you can get this backbone right in your modeling. Saying that, we also have to get our PyCoco tools, which is basically Coco. Uh, it's a package provided as a Python API that assists in loading, parsing, and visualizing the annotation in Coco. So this is really, really useful. We just have to import torch, detection, MMCV, etc. And it's good to have these versions in order to make sure it will be working in Colab. And then, so detection already provide high-level API to do inference and training. And here we already trained a model, so we'll just download our model, and as well as the checkpoint that we will use. So as you can see here, we will use mask RCNN with a ResNet 101 with I think like feature pyramid network, which combine low resolution, semantically strong feature with high resolutions, semantically weak features via top-down pathway and literal connections. We don't have to change anything for the configuration for the moment. We'll show you how to change like different parameters, tune your model, etc. But here we will use the checkpoint that we just downloaded here. So this is pre-trained model from detection. So this is also another powerful step from detection that they don't just give you the architecture, but also the pre-trained model. So you can do inference directly, or you can fine-tune this model in top of your dataset. So we'll use this demo image. You just have to do inference model that we initialize it here, and we put our image and we get results. Here we have also to specify the threshold. So if we have, I think we have to run it. Okay, so here, yes, it's downloading. And you can see here, for example, if we want to, here it's uploading the checkpoint. Sometimes it takes some time, but now it's done. And here it will tell you what is the minimum threshold for the classification that you want to show. Of course, if we choose a very high classification score, we will see that some object will be missing like this. You see, so only those who have more than 90% will be shown. But if we select only 10%, so we see a lot of object detected in the image. You see, we have more object detected. You can even make it lower, so you can see like I think you will have like 100 region of interest here detected around the image. Of course,
Yeah,
these are, yes.
Sorry about that. Can we go to the left table of contents and open the file structure and see if we have the model and config files properly downloaded? I think someone's getting error where the checkpoint file is not downloaded. So if you click on the left side, the very left of the screen, yeah, right there. So if you go to detection, configs, so they said, so which one are you missing? You're missing
I think
configs rest2net.
make the checkpoint. I think we should find it here, but okay, so.
Yeah, I think they're missing the config file, which is under configs rest2net. So you can do the same thing and check if it's there. So just click on detection. I think it's the detection.
Yeah, I think because they click, you know why? Because they click here collab. You see, you don't have to click collab here. You have to copy the link and put it, because here it will only copy this page. But when you put the link inside collab, it will extract all the packages and all the file that we have inside the repo.
Ah, I see. Okay, so yeah, maybe try just copying the link and
so just
see if that
copy
works.
the link from here, go to collab, and
so they can do it using this link in the PowerPoint, right? This should work, right?
yes.
Okay.
And just basically you will have it here with all the files, as you can see. Where is it? Yeah, but are you sure you run all the cells? Because here basically we should have the same.
You have do you have the file that you got the error from, the mask RCN one?
Which file could be missing?
So I think they said the rest2net, it should be under detection. So if you Eddine, if you click on the detection, yeah, right there, and then it should be under detection and then configs. Yeah, configs rest2net.
ResNet, yes.
Rest2net. Yeah, right there.
And basically mask
Mask
RCNN 100 FPN2.
It should be right there. If you don't see it, then
yes, this is it.
Yeah, maybe try the other method, opening the link directly and re-executing these cells.
I have the file, he said.
Okay, you have the file, but you're still getting that error. That's weird.
Can you restart the notebook? Maybe he click CD twice or something, you know. Just click runtime run all. So restart the notebook and click run all. Don't just basically run it one by one. Sometimes you run some cells twice, you know, and that's problematic.
Okay, so this should get you in the current directory, cd. So there's this cd command. Yeah, it might be that you run one of the cells twice.
Yes, that's right.
It could
So
be that case.
if he can restart the notebook and then run all the cells one by one, making sure that you don't repeat two cells twice. Because this should be working the same. Did others? Okay. Did others work for them? Did everyone have this image with the detection or no?
I think both.
I was able to run it.
I think we have at least 2 folks getting that error. Okay, so Rajiv had it working.
Okay, perfect.
Okay, yeah. So maybe just try rerunning it. Okay, awesome. It's working now. Yeah. So if you have any issue, just yeah, maybe restart runtime, factory reset runtime, and rerun again. Yeah.
Okay, so here basically we use the segmentation, but on the pre-trained model provided by detection. Okay, but for us, we want to use our own objects. We don't just want to detect the objects that are predefined by the Coco dataset of detection. which only contain like chairs, cars, etc. But we want to create our own customized dataset. So basically, to train a new detector, there are usually three things to do: support a new dataset, modify the config, and train a new model. In order to support a new dataset, there are three ways to do it. Either to reorganize the dataset into COCO format, reorganize the dataset into a middle format, or implement a new dataset, which is not not very advised to do it, because sometimes you will have some errors. We basically offered an example to convert both ADE20K dataset data from the MIT website, but also if you want to use your own label me generated custom data. So we have that in chapter 2. And now what we are going to do is basically to download the reformatted dataset from our link and visualize the data first. Okay, so we will just basically download the dataset. These are like images, okay, with their annotations. So you can see here the images. Okay, so we have all the images, and I will show you an example of this bedroom scene COCO image from the training dataset. You can see here also one, for example. You see, so we have like a different type of images, and you can see all of them. After downloading the data, we implemented EDE20K based on the COCO dataset. So we imported COCO dataset, and we created an ADE20K bed dataset, which is an inherent or subclass of COCO dataset, which contain all our classes. It contain door, door case, anything related to bed, floor, painting, pictures, window, anything. So all these objects we want to segment and detect inside our segmentations. Also, what we need to do, as I told you before, we have our configuration file, the one that we have an error. So this one, the mask RCNN2, you can modify this configuration file with your own parameters. How we can do that? I will show you how. Basically, we have this is the configuration file, and you can change all these parameters. For example, you can change the root for the training data, for the inference. Here, basically, we will use the same repo for train and for the test and the final inference, because we don't have like a final inference here. We just have validation. You also have to put your checkpoint file, like your weights of your trained model. So if you don't want to start from random weights, you can put either the path to the checkpoint file provided by ADE20K dataset, so the pre-trained model on COCO dataset. Otherwise, you can put your own weights here, where you are going to save the logs and the files. And here, different other parameters like learning rate, also the log configuration intervals, and what will be the evaluation model. So here we are basically choosing mean average precision as metric, but there are also different other metrics that you can use in order to evaluate your segmentations. And finally, we can also set the evaluation interval to reduce the evaluation time. And finally, we only going to train it for one epoch, otherwise it will take more time. So we just show you how you can train it for only one epoch for the moment. Okay, and you can see here, sorry, so yes, I didn't run this. And you can see all your parameters here, even those that we didn't modify. So also you can like modify different other parameters here. You can also modify the training. For example, here we have data augmentation already included into configuration file. So we are doing flip, image scale, transformation like random split, resize, normalize, etc., etc. You can do any other format of resizing and modification for your dataset. And finally, we can start training our model for one epoch. I hope that it didn't take a lot of time. So yes.
Sorry to interrupt here, Eddine. So while you're training the model, we can actually also go through, say if you want to train this model with a GPU locally or on your VM, how do you modify that those config files then? So Eddine, if you want me to cover that, so you can leave the cell running, training the model for
Yes,
just one
it's
epoch,
training right
and
now.
we can go through that part quickly. All right. I'm gonna share my screen.
Okay.
So yeah, as you have seen, we have done the config modification here. So this is because on Google Colab you can't just open a file and edit and save back easily. So that's why we're modifying these parameters directly using because the config file is basically a dictionary file. So you're modifying all these keys and values using these different commands here. But if you're on your desktop and you have a GPU and you train these models yourself, what you can do here is actually quite a simple process. So the details you can actually find in the README here. So training, yeah. So if you open this notebook right here, training notebook, and then you can see this is where we do all the installation locally, and then this is where you get the where you actually modify your data set and your can't see my screen. Okay, always forget. How about now? Should be able to see my screen now. So yeah, I'm just on this chapter 3 training notebook. It's a different version from the Colab version. Yeah, let me make sure. Okay, perfect. So so basically, these are just some installation instructions. You can follow the website. So the only thing to pay attention to when you want to install it locally is this part. Let me just point that in case you run into any difficulty. Yeah, so if you go to their get started, the only difficulty with installation here is you have to make sure that your CUDA environment, your GPU driver environment matches the PyTorch version. So you need to go to their PyTorch website and make sure your CUDA version matches the one that you're installing here. And then, so basically they give a few examples, right? So if you have 10.1, then you have to install it like this. If you have 9.2, install it like this. So there are different customized commands that you can find on the PyTorch website which will correspond to your CUDA version. So that's the important thing to note when you're installing it locally. And then in order to change the configs locally, so if you open this notebook right here.
Can you zoom a little bit because it's
yeah, sorry. How about now? Should be a little bit better. Yeah. So so if you go to this notebook training notebook right here, we'll have the instructions listed for how to modify these dataset and config files. So first, dataset file. So you have a customized dataset. You're training on your own customized dataset. Suppose that you followed all the instructions that we made for chapter 2, where you converted your dataset into a COCO format. Then it's really simple. All you need to do is go into this directory, mmdetect dataset directory, and create your own dataset file. And how to create it? Just follow this module right here. So from COCO, import COCO dataset, and then your new dataset basically inherits all its functions. And then you can just list all your classes here. It's not necessary this step, but I think it's better that you have it in your file. So this is a very simple file, just one line with the imports. And then what you want to do is you want to import this data set into your init.py. So let me show you what it looks like. So this is what your init file looks like. So you can see all these data set that I have right here. So these are all my customized data set. So I added all of them in these import statements. And then also include them below in this list. So all just put down your data set right here. So it's as simple as that, adding your own data set. Yeah, so this step, everybody should be able to follow really easily. And then next step before you actually start the training, the config files is what you need to pay attention to. So config files, they're like what Eddine introduced. There are all these different models, all these different backbones, networks, different parameters, and combinations of different structures. First, you can go into the model zoo and pick your own. Pick what config you want to use. Something that I like to do is like to go into this and compare these performances. So for example, if I'm trying to see if I want to use cascade, mask RCNN for segmentation, or if I want to use, say, mask RCNN, mask RCNN. So you can go there, and then you can look at their benchmark. So you can look at their mask AP. As you can see, it improves from based on these backbones. So this one is really good. And then you can also see that you have some different styles of models, which usually if you have and they're also based on if you have different schedules. This just means if you train longer, shorter, and some of the learning rate also changes in these schedules.
And also the inference time is sometimes very important.
Exactly, yeah. And if you look at this column, if you want to have a faster model, then yeah, basically right here, this one is really good, except it's really large. And then if you want to compare it with Cascade, then you just go into this right here, and then you can take a look. You can see Cascade actually does a little bit better compared to the numbers of mask RCNN. So this is how you pick your model. And then once you pick your model, you find the corresponding config file. So for example, I picked this one, right? So when I pick this one, I just look for X101 664 for the FPN. So it should be this one right here. So you can open it and just check it out. And as you can see, it's a very simple file because it uses a really nice structure. So it uses a really nice structure where you have the base model file. And then so this is how you follow it, right? You trace back, you trace up. So this specific configuration uses this base configuration. So now you just go into this configuration and you take a look. So this is just for initial purpose of learning how these structures work. You're not going to need to do this when you are used to how to modify these config files. You don't need to repeat all of these process. But when you first start, you want to understand how these work. So just take another look at this one. So yeah, if you look at this one, you can see it uses this base config file. So you keep tracing back. You go up one more level, and you can see now it finally gets to this one. So it's another base file. So you keep tracing, and this is what you have. So now this is the one sort of the final base file that you will get. So once you see this kind of structure in the file, you can see the base has the model base, the dataset base, and the schedule base. This is where you know you have reached the end. And these are actually the files that you actually need to modify. So how do you modify these? Very simple as well, actually. So let's take a look at the model base file first. So in your model, you have actually everything is covered under the base directory. So you go back to the configs, and then you go to base. And then these are your model base file, dataset base file, schedules base file. Your model space file, the one that we just looked at, is this one, scarcity in there. So you can see this is where actually the essence are defined. So all of the structures of the model, all of the transformations, the evaluation metrics, these are all defined in here. So remember one thing, and only one thing you need to modify in these base model files is your number of classes. So this is the only area that you need to modify in these base files. So you can see it's 80 because it was this network was pre-trained on Coco. Coco has 80 classes. So this is where you want to modify. Say we have, I think 12, maybe 20 classes, and then you just change that number 80 to 20. You can see there are actually 3 different places with 80. So modify all 3 to 20 to the corresponding number of classes that you have in your own customized dataset, and you're done. You're done with your model config. And then next one is your dataset config file. So dataset config file, it's a little bit harder to change. So for object detection, you want to change this file because that's what the base file the models will be using. Again, you can find out what it's using based on the final traced file that you see. So right here, you see it uses Coco instance.py. So for segmentation models, this is the dataset configuration file that it uses. And then, so what we want to do is just go into the Coco instance. And then as you can see, this is where it defines the transformation on the dataset and then where your dataset is. So these are the parts where you want to modify. The JSON file is your annotation file. Image prefix is what you define in your annotation file, your image names prefix. So in these JSON files, these are the structure of the Coco dataset, and you just redefine it with your own structure. Hope this is clear. But once you train one time with your own data, this will become very clear to you. And just compare this with what we did in the Colab version. So this is what we're doing in Colab version. So we're doing the same thing here, except we're using all these dictionary keys to achieve that because we can open the file and edit them and save back. So you can see data root, annotation file, image prefix for the training, validation, and testing. So this is what we're doing here. And yeah, we're basically doing the same thing here. And then in terms of the schedule-based file, usually you don't need to change it. So schedules should usually stay the same. If you say, if the model uses a 1x schedule, it's usually optimized for that model. But as you run your training, if you see that your model hasn't converged yet, then you can always go into these and change, the number of epochs that you're using, for example. But then there's one thing, actually there is one thing that you need to change, which is the learning rate. So MM detection also actually defaults that you have 8 GPUs. So the learning rate is a little bit higher than if you have 1 GPU. So for example, if you only have 1 GPU, you just divide that by 8, which should be 0.0025. And then if you have 2 GPUs, then divide that by 4. So no matter, depending on how many GPUs you have, change this learning rate so your model trains properly. But the total number of epochs should usually just stay the same because it's usually optimized for this specific structure. And we listed all of the instructions in this notebook here. Basically the same thing. If you go into the notebook, you can follow this example. We find the corresponding model file first for this mask AP 38.7 performance model, and then you trace up based on the model information, you see look at the base, and you finally trace up to the final base file right here. And then you can go into each of these directories to modify. So yeah, I hope this is clear for everybody, how to change the model files, model config files before you actually start the training. Definitely let me know if it's confusing. It's definitely confusing at first, but once you find out how it works, every time if you see a mask RCN model, if you have any backbone, you'll always change this file. So you don't even need to go to the actual config file and trace up the files. You look at the name of the config file and you see it's mask RCN in it, then that's the only file you'll need to change. Same goes with dataset. So once you change your dataset, it's always going to be Coco instance for segmentation and Coco detection for object detection. And schedule, usually, like I said, you just need to modify the learning rate. So don't worry if you can't figure out the exact epoch that you're going to use. Usually it works. All right, let's see. You have to check out detection if you want to fine tune. I didn't quite understand what you mean by checkout detection. Let me know if you want to specify some more details. But yeah, PyTorch is much more difficult to navigate. I would say it's really customizable. It's a really big library that you have many different options to customize. So that's why it's a little bit more difficult to navigate at first. But you get all these models. So these are really the top performing models for segmentation. And we're actually going to introduce a TensorFlow model in chapter 5, the mobile conversion section. But yeah, we'll see if we finish training here, Eddine. You want to take over the rest of chapter 4?
Yes.
Chapter 3, yeah. Let me stop my sharing.
Okay, so as you can see here, the training was done. And basically, you can see different metrics and different loss evaluations from basically how much memory the model took, loss RPN class. You can see also the loss of the class. So this is basically predicting with high accuracy each object inside the image, basically 90% of accuracy. The bbox is also great. So how much the predicted bbox comparing to the ground truth bbox around the object, but also the loss of the mask. So this is the loss of the segmentation or the area of the object comparing to the ground truth. And you can see here that we can see all these metrics together in this log understanding. Basically, we can have also an understanding of the training process and know how well the detector is trained. Of course, here we are only trained for one epoch because otherwise it will take more time. And then we can even get better results and achieve like 95% of accuracy or even better loss for the bbox on the mask loss. You can see here, this is the detection using one epoch. So we will run it over here. Basically, this is one epoch. It's not amazing, but at least we were able to detect the floor, the ceiling, the walls, windows, and the bed with a very good accuracy. And then what we did, basically, we trained for you this model for 18 epochs. We just basically going to download the model with the corresponding configurations. So we will run this model. One moment. So I think this is okay. So we just need to basically install the configuration and the checkpoint. It will not take a lot of time, so only 10 seconds. And then you can see basically we are calling the checkpoint after 18 epochs and the same configuration as before. We initialize the detector with the configurations and the checkpoint. We specify the device to be CUDA 0, basically the first GPU machine, and the same dataset classes. So basically, we'll use the same classes, and we can get the results where we will apply the inference detector on this image from the validation dataset, and we can see here that after 18 epochs, how much improvement comparing to the first one with only one epochs. And you know, in deep learning, whenever we train for more epochs, we can get even better results. Of course, we need to be aware of overfitting. And you can see that it performs much better than the model trained for one epochs. And then for model inference and image post-processing, I will let Cody to show you what he did.
All right, thanks, Eddine. Hope everybody got a chance to train their model for one epoch. If not, let us know what you encountered, what error you encountered. So I'm going to show you some
Just
output.
we have a question, Cody. So he
Yeah,
said how long it will take to train the model on 18 epochs. So for this time, it take 15 minutes for one epoch. So you can basically multiply 18 by 15 minutes, and you can get around 5 to 6 hours of training on GPU, of course, because Colab will give you access to GPU memory. And there is another question depends. Oh, okay, so you already answered. Sorry, I didn't see your answer.
yeah, don't worry. Yeah, so I think it depends on how fast your VM is too.
Yes.
Yeah, and how fast your GPU is. I think once you figure out how long one epoch trains, just like I said, multiply that by how many epochs you're training. Something that I want to show you really quick. So this is output from object detection model that I trained. It will be similar for segmentation model. So after each epoch, we're evaluating it on the validation set. So as you can see, this is evaluating on B-box. In segmentation, you'll see SEGM for segment. Oh, am I not sharing my screen again? Let's see.
I think so, yes.
Okay, there we go. Yeah, so as you can see, this one, it's showing the B-box result, and this is by epoch. So if I just go down the output, you can see after each epoch, you see the different numbers. It improves, and then at one point it starts to saturate. And then there's actually a very easy plotting function in MIME detection where you can plot the results. So you can see how the curve changes. And once you figure out it's saturated, you can select your best performing model. And these IOUs are just at each IOU threshold, 50%, 75%, how accurate your model is, your average precision. Yeah, it's quickly showing you how to read the output. But yeah, so what we're looking at here is we just downloaded this model trained for 18 epochs and tested our results. And next, we're going to do some post-processing. So sometimes what you want to do with some of these outputs is sometimes they're kind of rough. Even if you train your model to a very nice degree, very nice quality output, sometimes you still don't get the best desired looking output that you want. For example, say your purpose is to train a segmentation model and then crop that object out. For example, you want to crop out your bed and then run advertisement or list it somewhere else, post it on your on another image or combine it into another image. What you want to do, you can crop your bed out. But if you have this, these rough boundaries, these very jagged boundaries, it's not very nice. And then if you actually want to do some post processing, it will help a lot, do a lot better. So how do we make this work? So here we'll give a few examples. So first we load some of the necessary module. The key one here is the OpenCV. So OpenCV does a lot of processing on images using some traditional techniques. And here we're just defining some functions. So reading the image, getting the segmentation detail. So this is one function that we wrote that does some very simple post-processing. So what this one does is that it takes a contour of the object that you segmented and then approximate it to the number of corners you specify. So for example, if you want to output a rectangle or a quadrangle, it just means it has 4 corners, then you can specify it to have 4 corners here, and then refine it on your segmentation output. So so what this function does here is that it just loops through this approximated contour using OpenCV. So OpenCV first approximates it based on some initial parameter, and then you just keep looping and strengthen or weaken this parameter in order to get the final number 4 when you have 4 corners. So for example, running this on this image here, so we first download the image, and then we run the segmentation model. As you can see, it generates very decent output. You can get the windows here, the wall painting, and some of the floor. But it's definitely not perfect. Especially say, for example, if you, okay, so I think it's a little bit smaller. Trying to see if I can zoom in just a little bit. I think this may be a little bit better.
Yes,
yeah,
it's better.
Okay, so looking at here, actually, if I close this, it's better. So looking at here, if you want to, for example, crop out this wall painting, and you didn't get a really nice boundary over this wall painting. So we run this function that we just defined above here, this approximate corner, and then we just approximate it to 4 corners. Then what we do here, so this is just output, get the output for the segmentation and select the one that you actually want. So we want the picture frame detected, and then we get the actual segmentation corresponding to that picture frame. And then now we actually run the contour detection and the approximation, and you can see how nice we get the output is. And now you can actually crop this this painting out properly. And then let's look at another example. So this one actually just uses the OpenCV function directly called mean area rectangle. So mean area rectangle is just creates a minimum area rectangle that encloses your contour. So your original contour looks like this with some of these curved edges. And then if you draw an enclosing minimum area rectangle, what you'll get is this nice rectangle, which is just like this. These two are not exactly the same. It looks pretty much similar, but the bottom edge is actually a little bit slanted on this image. So this is just one use case for this post-processing technique. And so why sometimes do we want to choose, define our own corners rather than using some of these OpenCV functions directly? Here we demonstrated with another example. So let's run this one, download this image. And then now we're gonna look at this window. We want to crop out this window. So now you can use the OpenCV minimum area rectangle function directly, because once you get the segmentation for that window, which we'll do here, as you can see, it's some curved edges here and there. So once you get this segmentation, if you use the min area rectangle function directly, what you will get is actually just a rectangle. And it's actually contains some areas of the wall here, which is probably something you don't want if you want to just crop out the window itself. So now this is where our function comes in handy. We use so first we retrieve the segmentation corresponding to the window. And then we run this function and get the approximated contour. As you can see, it looks much better than the original. Still a little bit off on the bottom. It's because you have this right here. So instead of approximating it like this, you're actually approximating it like this. So this is just, we blame it on the segmentation model. But in any case, this demonstrates the usage of these post-processing techniques. And for a lot of different other use cases, you can think of, for example, you might want to say if you want to piece together different images and you want to use some in-painting techniques like Eddine mentioned in his talk, where you take one painting or one item and you want to merge it with another background. You can do that by using this approach, where you segment out the actual object that you're interested in, and then you do some approximation, and then you do some in-painting. So that should be the best pipeline to achieve this. And that's pretty much over for chapter 4, the post-processing techniques. Feel free to ask any questions, but for the sake of time, we're gonna quickly move on to the last section where we're gonna look into some approaches for converting these desktop models to mobile. So first thing we're gonna look at, if you wanna open this tutorials chapter 5. So this actually a note here is that the last cell of this notebook where we actually test the inference of the converted mobile model requires you to run it on Mac OS because it's a Mac OS model basically. So if you don't have a Mac, don't worry, you can still run the previous cells, but then you won't be able to run the last cell where you're actually inferencing with that ML model. So ML model is basically the iOS version of these deep learning models. So this is a standard format that iOS uses. So let's take a look at this notebook. So I opened it on my Mac environment, this notebook right here. So these are some dependencies that you have to install. So here we're actually dealing with a TensorFlow model because for PyTorch models, there's actually less support out there currently. TensorFlow models, they do have very good support because it's been out there for a long time, and we're going to demonstrate it with a TensorFlow model. But then for PyTorch models, there are some instructions online in MM detection repository too that you can find where you have some resources to convert it to something called see if I can find it here. Yeah, something called Onyx. So you have to convert your model to Onyx first, and then you convert it to ML model, which is the final iOS format. So here we demonstrated using the TensorFlow version, where we don't need to use that middle format. So as you can see, what we do is first we just install these dependencies. Very easy to install. TensorFlow might give some folks some issues, but usually it won't be a problem. And then once you install these, you can run all of these cells properly, should be able to. So the first cell just sets your CUDA visible to false, which means if you don't have a GPU, don't worry, we don't need to use a GPU. So we run this one, and then we import the necessary packages. The CoreML tools here is the conversion tool that we're that plays the most important role here. And then we download and extract a pre-trained model. So this pre-trained model is based on DeepLab v3. So I think we briefly mentioned it in chapter 1, where DeepLab is a TensorFlow-based library, and it uses a deformed convolution, which I think we also include some details in our PowerPoint if you're interested in learning about that. But basically, here we just download a pre-trained DeepLab ADE20K model. So this one was pre-trained on the ADE20K scene parsing dataset, the smaller dataset. And then we download it and extract it. So here, I think I already downloaded it, but just gonna re-download it again. It shouldn't take too long. Yeah, and then it downloads and extracts this desktop model. And now we're gonna convert it to CoreML. So CoreML, using the CoreML tools, we specify where the downloaded model is. It's a frozen inference graph. You can actually also do this using checkpoint files, but here we're gonna use a frozen inference graph. And then you specify your output path, which is your output path for your ML model. And then here we do some, actually, this part isn't necessary for everybody. So here we do some conversion of the output format. So we transform it into a 515 by 515 image in the, so in iOS apps, you have those little square boxes where you, square containers where you put your images. So this is the exact format that those containers use. And then you can, so here we just transform the model output into this format before we actually run the CoreML tools to convert the desktop model to the ML model. So now we run this. This conversion process is actually really fast. Just show you this. Let me also show you something else. So one purpose of what we're doing here is that we also want to make the models smaller on iOS, because on desktop, these models are really huge, can be hundreds of megabytes. On the mobile side, you don't want a model that big because your app will be overloaded, and isn't taking very long. Yeah, so let me check out that model. So as you can see here, the frozen inference graph is 158 megabytes. And if you look at the checkpoint file, it's 314 megabytes. So now, after we convert it to ML model, we can first check its structure. So this is just what you see here with the different input output. And then we're gonna save it to our output file path, which is, it should be right here. Yeah, the dplat.ml model. So this is our ML model. As you can see, it's actually the exact same size with the frozen inference graph. So how do we reduce its size? So what we do is called quantization. So quantization is a process where we transform basically the numbers, the weights in the model to a smaller representation. So originally we're using float 32, which means it's a 32-bit float for all the weights inside the model. With quantization, we can try to reduce these to smaller formats, and then we save some storage. So why don't we need all these accurate digits? Because on the mobile, it's usually a smaller screen, so your resolution is smaller on desktop. So you actually don't need all that resolution for it to work well. And then so this is why we do quantization. And so how do we do this? So quantization, I'm gonna run these two files, these first. So these are just changing some formats, and then we quantize the model here. As you can see, we quantize it to a 16-bit classification. So so we reduce the 32-bit floats of all the weights to 16 bits float. So what can we expect from the size in this case? Basically reduce it by half, right? So because we have a half-size representation of our weights. So we run the quantization. As you can see, does all these layers one by one. Basically, it loops through all these layers and transform all those weights into a smaller format. Yeah, it should take about a few minutes, but yeah, but then once it's done, we're gonna check its size and make sure it's smaller. I think we have a question for model size compression. Have you had a chance to try out? Not necessarily for iOS. No, that's a very good suggestion. We'll definitely check it out. Let's see. Yeah, thanks for the suggestion. All right, so now our model has finished quantizing, and we'll run some sanity check to make sure it's still the same, everything's the same format. And as you can see, actually right now it says in 32, which it shouldn't be in 32, but we'll ignore that for now. And then let's look at our model size. Yeah, as you can see, basically we got it reduced by half. Originally it was 158, now it's only 79 megabytes. How about the performance? Let's check it out. So let's test it on inference. So this is the last cell, as I mentioned. It only works on Mac OS. This is an image that we provided in the, it should come on with your GitHub repo. And then if you just execute this, it will actually run the ML model and produce the output. As you can see, it doesn't do super well, but it does a really decent job. You can see the boundary of the lamp here. You can see the couch, some pillows, curtains, floor, area rug. Yeah, so that's a decent job. And so as you can see, it comes in very handy with quantization where you reduce the model by half, but still get a nice output. What we should have done is actually compare the output between the two models, but trust me, they don't really differ, at least visually. And then one last thing that I want to show you is if you're interested in Android conversion, there's also actually a very nice page out there. Let's see, right here. So if anyone's interested, we'll also post the link here. So this is the TensorFlow-lite version of the same model that we just used, the DeepLab v3 model trained on 8020K. I'm gonna post the link here if you're interested in taking a look. But as you can see, they quantized the model and to basically a quarter of its original size, to only 40 megabytes. And I think they also provided a Colab notebook right here, where instructing how to convert that desktop model into TensorFlow-lite. So it's also a very simple conversion process. And they also demonstrated with a picture. Yeah, as you can see, the converted model still does a really nice job, the quantized model. So yeah, there you go. For this is all pretty much what we have for the model conversion side, and pretty much all we have for today. And I guess we're pretty good on time, so we have about 15 minutes. If you have any further question, definitely feel free to contact us even after this if you have more questions. But thanks for joining everybody to our workshop, and we had a great time. We also learned a lot from you guys. Hopefully you learned something out of this too. Yeah. And thanks for Ali.
Yes, thank you, Cody, and thanks to everyone for attending.
Yeah, thanks for everyone's comments. So this workshop, so there was an original version, previous version of the workshop. We presented it at KDD 2020. And then we modified this version to try to make it better based on the feedback we got from there. And also we added the mobile conversion because a lot of people were also interested in those. Yeah, but definitely got a lot of great feedbacks again today. So yeah, thanks everyone. And if we're good, I think we're gonna end here. And yeah, feel free to connect with us later. And hope everybody have a great rest of the conference.
And have a great day or night, depends on your time zone.
Yeah, have a good one.